So thank you everyone for joining. Good morning, I'm Jane Waterhouse. I'm working with C2O Consulting, contracted by RRRC to work on the NESP synthesis projects for the sediment and nutrient themes. I'm just going to give a introductory presentation. I need to turn off those notifications. So the purpose of this theme is to give an overview of the synthesis theme for the projects under the NESP program that are relevant to sediment research. So it's pretty high level, and the idea of this was really to give people an opportunity to hear a snapshot of the key projects that are contributing to this theme, and I'll give some conclusions at the end. I'll also start with a bit of an overview of the scope of the synthesis products that we'll be developing. As you can see there, we've got a number of presentations to go through. I'll be keeping time, and I'm going to have a bell at 10 minutes, encouraging researchers to stop at that point and provide an opportunity for questions. As Holton said, you can contribute questions on the chat function, and then I'll ask you to please stay on mute unless you're presenting or if it's during question time. So just a very quick intro to the Tropical Water Quality Hub. You're all obviously very familiar with it. I think now we can say that we're fairly confident that we've achieved that goal of conducting science that supports implementation of actions for better management of the Great Barrier Reef and the supporting knowledge to go with that. It is predominantly been Great Barrier Reef and associated catchments in this hub, and Torres Strait extending that far, and Coral Sea as well. It's about improving water quality, measuring the outcomes of those improvements in the GBR and the associated habitats. And it's really been very applied, and I can say with confidence that the projects in this session today have been highly collaborative with other programs and with each other. It's been focused on outcomes, and it has provided good interaction with the stakeholders and landholders, for example, from the outset. So the hub synthesis projects are an activity that's been implemented for the final year of the program. In total, there's 8. There's one around COTS, the restoring ecosystems from catchment to reef, overcoming barriers to reducing nitrogen losses to the Great Barrier Reef. This one, which has reduced the end-of-catchment fine sediment loads and ecosystem impacts, improving coral condition, which is a bit more about the research within the GBR itself, looking at agricultural practice change through behaviour change projects and establishing trust frameworks. And then the last 2 are a bit more sort of hub-wide in terms of the impacts, and then across the whole NESP program, linked with the other hubs as well. So very quick background to the sediment theme. There's lots of words on this slide. I just wanted to highlight a few key points though. Why are we interested in sediment research? So as we know, declining water quality from the adjacent catchments is a really important contributor to the poor state of many of the GBR ecosystems. Water quality improvement has a really important role in ecosystem resilience, and that's something that we can't let fall out of our minds when we're thinking about how can we manage the reef when we've got threats like climate change looming. There's other stresses we can reduce, and water quality is one of them. Fine sediment is one of those stresses. It poses a risk to seagrass and coral reefs and other ecosystems, largely through light reduction, but other factors as well. We have large loads of sediment coming from the catchment. That's increased a lot since European settlement and clearing of the catchments. We know that it's the fine sediment that's the most important component in terms of impacts on the Great Barrier Reef. We know that a lot of that comes from grazing lands, or those areas associated with those, particularly in the Burdekin and Fitzroy, those large dry catchments. But sediment yields can be high in some locations and some land uses, but it's fairly localised. We know it's about subsurface erosion, so gullies, stream banks, steep rills on hill slopes, they are the primary contributors of that fine sediment. We also know, unfortunately, that the progress towards reducing those loads from the catchment has been slow. So in the scientific consensus statement a few years ago now, but it's still very much the same message, is that management options need to be cost effective and targeted. We haven't got enough money to manage everything everywhere. And in order to do that, we need to continually support our knowledge and ability to select the most appropriate solutions. I can say with confidence that the NESP sediment related research has contributed to doing that. So they've focused on the source, fate, transport and impact of sediments on estuarine coral and reef ecosystems. Here's just a few highlights of the scope of the work. So refine the understanding of sediment dynamics of from the catchment to the reef, and that's a really prominent factor in this set of projects, is that they have been linked. Looking at the impacts in the receiving environment, what do we understand about sediment suspension and the impacts of activities such as dredging. We've looked at where sediment disperses in the marine environment and how to better measure, monitor and report on that. We've simulated changes to environmental conditions as a result of sediment inputs using modelling, and assessed the implications of that on seagrass communities. We've used tracing techniques to investigate the most environmentally relevant sediment characteristics and sources. And finally, there's been a big chunk of work looking at remediation methods for gully and stream bank erosion. Within all of that, there's been some new methods for measurement and evaluation of water quality outcomes, and you'll hear a bit about those today. In this final year, we've developed, as I said, we've got this synthesis project. The main output from that is the technical synthesis report. It provides a summary of the key findings. It's an expanded version essentially of what we're hearing today, and with some combined outcomes or integrated outcomes. We have an interactive website, so there's main pages representing each of the themes with an interactive component that allows you to access additional resources and links you back to other pages, including the standard Tropical Water Quality Hub website. There's a bit of an overview of that website on the 11th of December. And then we've got a bunch of case studies. So the outcomes from those will be incorporated to the website, and a number of published outputs like brochures, hopefully some video animations down the track. The diagram you see down there below is our current version of the main page of the website, so that gives you an idea. There will be interactivity where you can click on elements of that landscape, and it'll take you to a story from the research that tells you what we've learned about that component in the sediment catchment to reef story. I'm just going to touch on the case study topics today, so I'll introduce them. We're not presenting the results of those at this stage, and that's something that we'd like to do once we've got all the results collectively. So we've got, I think, 5. So the first one is looking at modelling light and seagrass interaction. So Barbara and Catherine are combining the results of their 2 projects and the tools and learnings from those as well to assess seagrass species distribution under the different catchment load scenarios. So using A-reefs modelling scenarios and assessing the influence of benthic light on that. The second one is really the sediment story. So Steve and Zoe are giving a refined understanding of the most important characteristics of land-based sediment and particulate nutrients. So it's really about sitting in the manager's seat, what do they need? What have we learned that they need to know about targeting sediment management in the catchment, based on what we understand are the most important impacts then in the marine environment. The third one is about gully management. So the program has done a significant amount of work learning about remediation options. Beck and Andrew are preparing I guess a simple summary of the key findings relevant to current and future gully management projects. And so that includes also transferable learning. So not just the work that they've identified in the Cape York and Burdekin catchments, for example, but from that, what have they learned that can be applied elsewhere? So I see that as very valuable for future investment programs. We're going to do a summary of innovations in monitoring. So how NESP projects have developed or utilised new technologies to better measure and evaluate water quality outcomes. So there's a raft of examples throughout the projects that will be able to summarise that. And then finally, a sediment to sea story, source to sea story, focusing on the Burdekin catchment. So a large part of the work has been done in the Burdekin. So we've got a great opportunity there to use the interactive website to just show how those parts of the story link together. So I think we're on time now I just wanted to give that introduction to provide the context. Now we're going to hear from each of the researchers about the highlights of their projects, the outcomes of which feed into those synthesis case study topics and the technical synthesis report. So as you see there, we'll hear from Barbara first, talking about her Benthic Light project, followed by Catherine, looking at the seagrass in response to light work that they've done. Steve will talk about the importance of sediment quality, the work that he's been doing with Zoe and others. We'll have a 15-minute break to go grab a cup of tea or whatever you need to do, and then those that want to stay could ask specific questions if they wanted to, and we'll come back to hear more about the management side of things from Rebecca and Andrew before I give my version of the highlights and conclusions at this point. So I will stop sharing my screen and I'll hand over to Barbara. Do I do that?
So I'm going to be racing through several years of work, but for those who want more information about the details and the methods, some of that's already been published on the NESP website and in associated journal articles, and some of it will be coming out very soon in our final report, which is currently under review and due for submission on the 10th of December. I'm going to be talking about projects 2.3.1 and 5.3, and just a teaser of the work that I'm doing with Catherine Collier's team for the synthesis project. And I'd of course like to start by acknowledging the traditional owners of both Great Barrier Reef lands and the land from which I'm speaking today, the Ngunnawal people, and pay my respects to their elders past, present and future. I'm starting on the right-hand side of this diagram with the marine impacts of sediments, and how can we better monitor that so that we can better manage it in future. Although sediments, particularly in the near shore region, can impact benthic habitats in a few ways, one of the biggest ones is the impact of sediments and the nutrients they carry on the light environment in the Great Barrier Reef. Okay. How do we monitor this sort of thing currently? As I'm sure most of you know, each year or so the Great Barrier Reef Marine Park Authority and the Office of the Great Barrier Reef put out a reef report card under the Reef Plan. And that includes both catchment and marine reporting. When it comes to water quality, there's currently two indicators. Secchi depth, which is the depth which light penetrates from the surface, and chlorophyll A. And while these are useful indicators of water quality, they can sometimes be a bit hard to relate to exactly what corals and seagrasses are experiencing where they are, because that depends not just on the Secchi depth, but also how deep they are and in the water, and how well adapted they are to their conditions locally. So for this project, we know that the amount of light that reaches benthic habitats at the surface of coral reefs and seagrass beds is really important for the health of those habitats, and it can vary from year to year and season to season depending on weather conditions, and what's coming in from the catchments in particular. How do we better monitor that on the scale of the whole Great Barrier Reef? Obviously, the Marine Monitoring Program does great work up and down the nearshore region, in particular with direct measurements, but they can only get out a few times a year and don't really get out to the waters further out. So our aim in these projects was to develop a new index for water quality, a new indicator that could be an input to a water quality index that can be applied over the whole Great Barrier Reef, relates directly to ecological impacts and the conditions experienced by corals and seagrasses where they are, considers the chronic effects of light stress over a season or a year, and can be used in routine monitoring and reporting. So there are a number of steps to do that. And again, I'm just going to be touching on each of these steps quite briefly. First step was to work out in more detail exactly how corals and seagrasses respond to different light conditions. The second step was to develop an algorithm so that satellite ocean colour observations can be used to estimate BPAR, which is benthic light, across the whole Great Barrier Reef, to complement and extend what we can measure with direct in situ measurements. The third was to combine those pieces of information in a way that produces a readily reportable and trackable index of water quality in each NRM region or water body. And finally, to actually assess this index to see whether it can be used to predict ecological outcomes. So the initial work led by Caterina Fabricius did a lot of experimental work in the CSIN facilities, better pinning down how corals, in particular, they looked at 3 species of corals in both adult and juvenile forms, responded to a range of different light conditions to try to better pin down thresholds that we would need to look at in the index. And alongside this work, we also conducted a review of the literature to look at thresholds relevant to seagrass species that are important in the Great Barrier Reef. That work's been published in the 2.3.1 report, and some of it's been published in peer-reviewed journal articles, which are linked to from the website for the project. Second step was to develop a remote sensing algorithm to estimate benthic light across the whole Great Barrier Reef. That's formed the PhD project of a student working on this project, Tess Canto, and has been published in the last year or so in the journal Optics Express. But just to give you an idea of how it works, looking at the colour of light that's reflected back off the surface of the water to ocean colour satellites, we get an idea of how different wavelengths of light are being absorbed by the water as a result of the sediments and phytoplankton and so forth in the water, and can propagate that down to the depth of the bottom to work out how much light is actually reaching the bottom. That's been validated against in situ data for mostly mid-shelf sites and performs very well. Using that information from the instantaneous measurements from the satellite, we can extrapolate to work out how much light is reaching every 1 kilometre pixel on each day of the year when there's sufficiently clear conditions that aren't obscured by the clouds, and produce maps like this for each day or each month of the year, which just show how much light is getting to the bottom in each area. Finally, how do we use that together with the light responses to get an index? I'm not going to go into the details of the method that we came up with, but I'll just briefly say that we started by producing daily and then seasonal and annual maps of the amount of stress that would be experienced by benthic organisms in each pixel of the Great Barrier Reef as a result of light that is less than it could optimally be with perfect water quality for that, or at least water quality as good as could be achieved in that location. These light stress maps do show that there's considerable variability from year to year depending on what else is going on in the system, and from season to season. And using the data from each pixel in those maps, we aggregate to get a value for each NRM region and water body that we can then convert to a grade for each region that we can track over time. This figure is showing, I believe, the wet season grades for each region, from Cape York at the top to the Burnett Mary in the south, and from the very near shore enclosed coastal region on the left to offshore waters on the right. And as you see, particularly in the near shore regions and to a lesser extent in the mid-shelf, the index is sensitive to year-to-year variations, particularly in river discharges in each area. And whereas offshore and further north, you get more consistently good water quality and water clarity. So reduced water clarity is less likely to be impacting reefs in, for instance, the offshore Cape York.
Barbara, 5 minutes.
Right, thank you. Nearly there. Finally, to have some confidence in recommending that this be used for monitoring, we wanted to assess how good this index is in predicting ecological outcomes. And so I've very recently been doing some work together with Angus Thompson of the Marine Monitoring Program and Catherine Collier's team. Catherine will be speaking next, to look at how predictive the light stress maps and the regional index values are of coral health and changes from year to year in coral community resilience and seagrass distribution and community composition. So this work hasn't been published yet, but will be in the report. And I just have to, what we found is that when you take out the acute impacts due to things like bleaching events and major storms, and look at the remaining year-to-year variation between monitoring, we can use the coral index, which the MMP has recently developed as a collective measure of coral community resilience at each site, to see how much this light index predicts year-to-year changes. And we see that in some regions, particularly the near shore wet tropics and Fitzroy, and the mid-shelf dry tropics, the light index explains up to 43% of the remaining variability in that coral community resilience measure, while in a few other areas it's not really explaining the variability, which may mean that changes in water clarity aren't really important in determining coral responses in those areas. This is output from a random forest model, which is a statistical method that, among other things, can tell you how important various variables might be in predicting an output. And from this, we found that the new Benthic light index is a better predictor of that change in coral community resilience than any of the other proposed water quality indicators that we considered. River discharge is important, but but the Benthic light index is capturing that impact along with some other effects, and it's performing better than chlorophyll A, for instance, or non-algal particulates, which are a measure of sediment concentrations. Final slide. Just a very brief introduction to the work looking at seagrasses. We found that for some seagrass species, Benthic light is a very good predictor of what seagrasses will be present or absent in a particular part of the Great Barrier Reef. So we can use the model to predict seagrass community composition in those areas. And perhaps and potentially how that will change under different catchment management scenarios. I was wrong, it wasn't the final slide, but I'll finish very quickly. As well as using satellite observations, you can also calculate the Benthic light index from eReef's model output. When we do it, we find that it produces an index with a very similar predictive performance to the satellite observations, although the Benthic light that's predicted isn't exactly the same. And that means that we can use eReef scenarios to predict impacts of catchment policy change. Here's an example where I've done that, comparing 3 potential catchment management policies with current land management and its impact on the Benthic light index. And in this analysis, we find that it's only full adoption of innovative land management which is likely to make a significant difference to this particular indicator of health, though there may be other benefits from through other mechanisms of other, slightly less improvement. So from this project, we're able to map Benthic light and stress due to chronically low light or chronically reduced light conditions over the whole Great Barrier Reef. The new index that we've developed reflects the measured and ecological requirements of corals and seagrasses, so it relates directly to ecological impacts. It is responsive to year-to-year variations and regional variations in water quality. It is predictive of seagrass and coral metrics, and it can be used to predict ecological responses to policy change for the Great Barrier Reef. Very quick thanks to the rest of my team. Thank you very much. Jane, back to you.
Great, thank you, Barbara. That's fantastic.
Well, thanks everyone. Today I'll briefly touch on some of the work we've been doing and are still continuing on responses to light and on connecting sediment loads to outcomes for seagrass. I'll be talking primarily about project 3.2.1 and the extension project 5.4. There are a number of components to these projects, some of which I discussed in the webinar yesterday on the seagrass communities. There have also been a lot of people involved in different aspects of the projects, so I won't be going through the entire list. I would like to specifically mention Vicky Lambert and Kate O'Brien from UQ, who are the lead and senior authors on the Cleveland Bay case study that I'll talk through. And these projects were put forward by the Seagrass Group at Tropwater, but we've really relied on the support of sediment and water quality scientists. So I'd especially like to acknowledge Zoe and Steve and John Brady as key collaborators, particularly on the Cleveland Bay case study. The work also builds on a couple of previous NESP projects, a mapping synthesis and a light thresholds synthesis. So early on in the NESP program, we undertook a synthesis of seagrass light thresholds. This was focused on short-term light stress, which can be applied in compliance monitoring for dredging as an example. You won't be able to read this table at this scale, but it outlines light thresholds and suggested management thresholds and tolerable durations for exposure of most species. The light thresholds were used by John Burdekin and others to develop the current sediment load targets in the water quality improvement plan. But we really need to know much more about how sediment and light affects seagrass communities over longer timescales. So the objectives of Project 3.2.1 were to define communities and desired state for seagrass, which Alex Carter and I discussed in a webinar yesterday, so I won't go into detail of that today. Then examine the relationships between catchment inputs of sediment and seagrass in Cleveland Bay and identify critical thresholds or targets. And then finally to compare these to the existing load targets. We undertook a case study in Cleveland Bay, which is near Townsville. Image A shows the Burdekin catchment in yellow and Cleveland Bay in the inset box. Image B shows Cleveland Bay near the top of the map and the smaller rivers and creeks that also influence Cleveland Bay. The satellite image shows the Burdekin River plume during the 2019 floods. In that year, the plume first headed offshore to the reefs, as pictured here, before being pushed north towards Cleveland Bay, which is typical. So in order to connect sediment loads to outcomes for seagrass, we first needed to define what those outcomes were, and that is what conditions should seagrass meadows be in, which we refer to as desired state. Then we can investigate the loads that are associated with that desired state. So this map shows 9 communities that have unique species assemblages and environmental settings. Each one of those points represents on the map represents a site, of measured seagrass. They were identified using statistical models, and then desired state of seagrass area and biomass were identified. So this data comes from the Port of Townsville funded long-term monitoring program, which is carried out by Tropwater. And the data were collated for a previous NESP synthesis project. And it was updated for all data in the reef up to 2018 for these projects, and it's now available on eAtlas. The meadows are typically surveyed once per year in the dry season in Cleveland Bay, when seagrass biomass and area are at their highest. So I'd like to point out the purple points on the map, which are the shallow subtidal community. We assume and even show that subtidal seagrasses are more sensitive to sediment and low light, and so we focused on this community. Oh, there we go. There is a deeper community in Cleveland Bay, which is the pale orange points. However, this particular community is not routinely sampled, and so we couldn't examine long-term trends for that community, so we focus more on the purple shallow subtidal community. So today I refer to suspended sediment loads as TSS loads, which are the monitored loads that are less than 63 micron. Discharge and TSS are measured for the Burdekin and Horton rivers and were estimated, thanks to Steve, for all the other rivers and creeks influencing the bay. The grey bar is the discharge for the Burdekin River, and the coloured bars are for all of the other smaller catchments. So the Burdekin dwarfs the discharge from these other waterways. Now, previous monitoring and modelling by Zoe and others have shown that about 10 to 15% of the suspended sediment that load moves beyond the vicinity of the Burdekin River mouth. So TSS loads that are actually reaching Cleveland Bay were estimated based on this and the direction of the plume moved in each year. And our later analysis showed that including these estimated loads from the other creeks and the delivered load from the Burdekin River didn't improve our particular models. Therefore, from here on, we focus on just TSS loads for the Burdekin River only. So those TSS loads are indicated here by the crosses. In this data set, the highest TSS loads were in the 2008 to 2009 water year, yet the highest discharge was in 2010 to 11 in the year that Cyclone Yasi came through. So I've now overlaid the seagrass area in Cleveland Bay to this graph. We have the red line indicating area of all seagrass, and the blue line indicates that shallow subtidal community that I pointed out before. The largest area occurred during the data set that we have occurred in 2006-07, and 1 decade later in 2016-17. And there was a huge decline in seagrass area over the 4 years to 2011, and then it recovered. And the influence of river discharge and TS loads on this trend is without doubt. But there is a lag in the seagrass response to loads as well. As an example, in 2012-13, the TSS loads were low, but the seagrass area was also low because of the legacy effects from previous declines. So unfortunately, this seagrass data set doesn't include 2019, when there was a return to high discharge and loads. The seagrass was surveyed, but our analysis was completed before that data was available. So the relationship between seagrass indicators and loads was explored further. We used multiple discharge and load indicators, some of which I've already referred to, including multi-annual loads, delivered loads, and loads for all the creeks and rivers. We also used a number of different seagrass indicators, including area and biomass of the total seagrass community and the shallow subtidal community, and inter-annual change in these indicators. Correlating these load and seagrass indicators resulted in a flood of different models. Those with the highest correlations and those with less uncertainty in the indicators themselves were then chosen for calculating thresholds. And this figure here shows the correlation between seagrass area and the 4-year Burdekin River load, and desired state is shown by the orange line. The predicted TSS threshold to meet desired state is shown by the arrow, and the confidence bounds by the box around it. I'd like to point out that the confidence bands are quite large, owing to the fairly small number of years of data that we actually have to contribute to this analysis. We found that interannual change in seagrass indicators and multi-annual loads were better for connecting sediment loads to seagrass than simple annual correlations. And this is because, as we saw on the previous graph, there are lags in the way the ecosystem responds to sediment loads. So the next step was to relate these thresholds to the targets in the WQIP. To do this, the thresholds for TSS were converted to fine sediment loads and to percent anthropogenic load reduction. This resulted in load estimates that range from 38 to 49% reduction to meet the seagrass desired state. Given the uncertainty in these estimates, this can be considered within range of the existing target of 30% reduction in sediment load. So combining our results with existing WQIP targets is building evidence for the targets that have been set in a kind of an ensemble approach. There are a number of practicalities that made it challenging to connect sediment loads to seagrass outcomes at this scale. It's a very data-rich region with 12 years of comprehensive seagrass surveys to inform the analysis. But when the seagrass data from the late dry season is related to loads from the previous wet season, it's condensed down to essentially just 12 data points for each community. So we ran simple correlation models on these data, and these models don't demonstrate cause effect. We can't prove that the sediment loads caused the change in seagrass. They also can't include sediment dynamics and cumulative stresses because the models would be too complex for the data, and suitable data were not available at the time. Furthermore, we have only one period of significant events in this data set. The other main challenge is that it's a complex bay. We spent quite a bit of time exploring simple habitat suitability models for the bay that could link loads to light and to seagrass distributions, but we were unable to confidently apply them at that stage to ERTs. So I haven't shown those here today.
5 minutes, Catherine.
Okay, thank you. Just a couple of slides to go. So the analysis in Cleveland Bay was a case study, but high turbidity occurs across much of the distribution range of seagrass. This image here is from Princess Charlotte Bay in Cape York as an example. Therefore, we've upscaled our data synthesis and community classification to the GBR data set. This map shows a compilation of more than 35 years of seagrass data. Alex Carter and I spoke about this yesterday, so I'm not going to go into detail about it. But we can use this data to explore further analyses linking seagrass responses to light and sediment loads. As an example of the analysis we're undertaking with this data set, together with Barbara, we have these species distribution models, which have been developed for a number of species on the reef by Alex Carter and others. This image shows habitat suitability for one species, Halophila decipiens, as a kind of a heat map. So warmer colours indicate higher suitability for the species to occur there. This is underpinned by response curves to a number of different environmental conditions, including light, and Barbara showed an example of those light curves earlier on in her slides. These image scenario A and B show a prediction of how catchment management scenarios influence benthic light, and we'll use these to test the influence of those scenarios on seagrass habitat suitability. As Barbara previously mentioned, we're also exploring how well the new BPAR index can estimate seagrass habitat suitability using these species models, and we're also investigating changes in abundance as measured in the MMP. But all of that work is in progress. So with that, I'd like to thank you for listening and hand back to Janie.
Good morning, everyone. Hope everyone's well, and thank you for the opportunity for allowing me to present today. I'm giving a very quick overview of the project, which is really a 5-year project through project 2.1.5 originally, and now project 5.8. This work was led through Tropwater James Cook University, but also collaborators with the Department of Environment and Science and Griffith University. And really we're looking at working across the whole catchment to reef area to provide sort of support for the sediment dynamics, and offshore in the marine environment to provide some extra support for work like Barbara and Kath are doing, and also provide some support on looking at potential sediment sources in the catchment for the guys working up in the catchment. So we're trying to work across that whole catchment to reef story. And through this project, we've really been sampling across the catchment, trying to understand the soil particles that we come across in the catchment, how they are transported through the system, and then as they start moving offshore, looking at the various processes that are occurring for them to form like large sediment flocks, and looking at how we can trace those different components of the flocks. So as the sediment moves further offshore, they start becoming quite complex, what we call sediment flocks, which is a mixture of mineral particles, bacteria and fungi, phytoplankton and things, and other organic matter. And they can also release dissolved inorganic nitrogen as that bacteria reworks that organic material. So a lot of the tracing that we've been doing is on the inorganic mineral particles. We're looking at various components there that you can see on how we can trace that back to a catchment source. We're looking at various organic tracing, and we're looking also at the microbial composition of that's helping form these sediment flocks. I don't have time, of course, to go through all of this today, but just to make you aware, this is really our main aim of the project. What I'll really do today is present a large amount of the marine component. We've just been really working up a lot of this data for the final report, where we've established several logger sites, looking at a longitudinal gradient from the Burdekin River mouth up through to more the Palm Island group, where we've got a series of instrumental loggers like a nephelometer that's taking continuous 10-minute readings of turbidity, light, and light wave pressure, as well as a current meter and array of sediment traps to capture the composition of the sediment over that deployment period. So essentially, we're trying to examine the spatial and temporal variability of the sediment exposure and composition over these range of sites from the Burdekin, and we've also got a site off the Tully River off Dunk Island, a couple of sites up there that you can see. So I don't have time to go into that today though. And really just a broad summary of those results is we can define probably 3 paths of impact of how fine sediment can and the associated nutrients can impact some of our inshore systems of the Great Barrier Reef. And we can't, I'm not going to read all of this out, you can read it off the screen, but essentially the first one is the increased suppression of light in shallow turbid environments, which supports some of the Cleveland Bay case study that Kath just presented there. The second one is looking at like more pulse delivery, where the impact of the suspended sediment is really confined during the flood period, but then we can also start considering what else happens afterwards. And this also has a nutrient story as well, which I'll give you an example. And the third one really looks at chronic persistent turbidity, where the tourism industry contacted us to do some work in the Whitsundays, where they believe they've had some chronic turbidity issues down there. And I'm just putting up just an example there that probably provides some support for Barbara on moving towards more of a light metric. So first up is looking at this increased light suppression using Cleveland Bay as an example. And this is our logger data. So I'll quickly just walk you through this. This is the bottom panel is a river discharge from the Burdekin River. So we've deployed these instruments in 2016. We took them out in March 2020. And over that time, we've had a few floods from the Burdekin in 2017, which didn't really come up into our area. The plume largely moved south then. A plume in 2018, a flood event, and the big 2019 floods, which weren't just the Burdekin, but also quite significant flooding in Townsville, if you recall as well. Also, the orange panel is the suspended sediment concentration. So this is our turbidity logger, where we've done some calibrations between turbidity and suspended sediment concentration and established that relationship and converted that to suspended sediment concentration. This is the RMS pressure gauge, which essentially is measuring variability in water depth and the influence on pressure on the site. So it's thought to be a measure of the roughness of the conditions and the potential for resuspension. This is the light conditions from the logger. So we can see periods where there's very low light, where the logger essentially goes back to zero. So there's no light reaching the bottom. And just to give you an example, this site is in 5 meters of water too. So it's quite a shallow site. And then we have our normalized sediment accumulation rate that we measure in our sediment traps. So the sediment traps are out there for roughly about a 3-month deployment period. We measure the amount or mass of sediment that we've collected in the traps over that time. We divide that by the area of the trap head and divide that also by the days of the deployment period. So we calculate essentially a milligram per centimetre squared per day accumulation rate. Now what we can see is with the Burdekin flood in 2018, we have the highest suspended sediment concentration that coincides with that flood. And then in 2019, we had this very large resuspension event that happened prior to the 2019 flood event towards the end of December 2018. This was associated with ex-tropical cyclone Penny that came through the area, where there was virtually no discharge of the rivers, but very rough conditions in the bay. And you can see there's quite a large resuspension event occurring there. But again, the second largest peak in suspended sediment concentration coincided with the 2019 floods from Townsville and the Burdekin. And if we focus primarily on this period, actually, we can see that coinciding with the resuspension event prior to the flood, we had the light drop out for a period of about 15 days where there was virtually no light. We had no light for about 17 days during the reaching the bottom for the big 2019 flood event. And then we also see for relatively like small resuspension events that have occurred previously, as you can see in the green spikes, that certainly nothing higher than what we'd seen previously. We seem to see elevated suspended sediment concentrations in the events following the 2019 flood, where light also drops out for considerable periods as well. Now, on the sediment accumulation rates, we see the highest accumulation rates occurring as coinciding with that resuspension event and the flood, and also are quite elevated accumulation rates in the trap for that period following as well, that supports this increased suspended sediment concentration. So it provides some support that the new sediments come in, it's stuck around in the system, it's become more easily resuspended and influence the light regimes at this site, which is supporting what Kath is saying in the previous talk. So the second one I want to quickly talk through is the pulse delivery of flood plume sediment and particulate nitrogen using our Havana Island data series as an example. So same setup with the logger data, I won't go through that again, but just to point out what we see here is the highest suspended sediment concentrations, again, coincide with the 2018 and 2019 flood events that we see in the record. However, this is a little bit different. We don't actually see the large influence of the resuspension afterwards. So it shows that in this case anyway, the sediment that's come through to this site, it hasn't become available for subsequent resuspension after this period. And the sediment trapped accumulation rates seem to support this, because the next accumulation rates after the flood period actually reduced quite back to levels where there hasn't been really much influence at all from flooding. So what do we see at this site though? The really interesting observation that we saw is this site typically has quite high coral cover. So this is a typical example of what we see at the site. But following that 2019 flood event in particular, when we came back in June 2019, following that flood event, we actually saw quite thick coverage of macroalgae at this site. So what we'd hypothesize here is that new sediments come in and it's helped trigger this macroalgae bloom. Now the good macroalgae coverage, the good news story here is in the following deployment, that macroalgae had largely receded and the site was more back to that high coral cover that we saw. But I guess the story there is if we had other stresses acting in this environment, that this macroalgae cover potentially could become more persistent. So providing some of the support here as well is looking at the work that Zoe's really put together in the flood plumes, where we've looked at a transect moving up the coast and looking at how the sediment changes through the flood plumes. We can see this is what the buckets of water look like. And as you can see, as we move through, the water clears up quite a lot. There's still quite a lot of sediment in that water, even though it doesn't look like it though. And the sediment changes to become more organic rich, greater, finer particles, less than 20 microns in size. And we start seeing more sediment flocks forming and diatoms and things like that forming in the system. And this organic rich sediment is also quite nutrient rich as well. And moving on, the other colleagues from the Department of Environment and Science have actually started to quantify the amount of dissolved inorganic nitrogen being released from the plumes. The first step is when the sediment first hits the seawater, the ammonium that's absorbed onto sediment particles is essentially released. So this is a form of release of dissolved inorganic nitrogen, and they've quantified that amount being released here in the 2017 and 2018 Burdekin floods. And as that sediment moves further offshore, we start seeing microbials, communities such as fungi and bacteria starting to work on that sediment and rework the particulate nitrogen associated with the organic matter and converting that to dissolved inorganic nitrogen. And essentially the study here shows that quite considerable amounts of dissolved inorganic nitrogen can be released in the plume during this time, and even in the period following the plume. This process seems to continue for weeks afterwards with their incubation experiments. So that could provide some of the extra fuel for the macroalgae. Colleagues at Griffith University have also been studying the microbial composition of the sediment flocks as well, and it's largely bacteria. So as the plume moves further offshore, we see higher bacteria to fungi ratios associated with the sediment. And as the bacteria is working this organic matter, the organic matter becomes more what we call recalcitrant as we move further offshore. So that means it becomes less bioavailable for working. Now, I've just put this slide in, is some of the work we've been doing in the Whitsundays. I don't have time, obviously, to go through the whole kit and caboodle of the story. But the key point here is we did some work there looking at samples from the outer islands and inshore islands to do some tracing work as well. The key message here is in the outer island sites, we see suspended sediment concentrations here, which is represented by the bars of around about 0.5 milligrams per litre. If we go to the inshore site, it just increases by around 1 milligram per litre. And the difference in Secchi depth goes from about 9 to 9.5 metres down to 4 metres. So you can see really a small rise here in suspended particulate matter of around 1 milligram per litre can reduce that Secchi depth considerably. So that really supports Barbara's move to go to more of a light metric rather than taking these sort of more suspended sediment and turbidity type measurements, because they're like a small difference can mean quite a big difference in depth. And this is just a natural gradient through the Whitsundays. There's talk that this has become more, the chronic turbidity has come in the last 10 years or so, and we've sort of been working on that to work out the source of that. But I just thought I'd just point that out. A small change in suspended sediment concentration can mean a big change in Secchi depth. So looking at the identifying the, these sediment sources that can cause the most impact, in summary, it's really the fine, less than 20 micron organic rich sediment that travels the furthest in the GBR and has the capacity to release the dissolved nutrients and influence turbidity and potentially drive some macroalgae blooms in the inshore GBR. And some of the preliminary tracing work that we've been doing, looking at some of the radionuclides at the end of the Burdekin River at the Inkerman's bridge site, as well as samples from the Burdekin plume, which you can see in the red and green dots. There's very little cesium-137 in these samples, so it immediately tells us these are subsurface erosion sources greater than 15 centimetres below the soil profile is where the sediment's coming from. So it really confirms a lot of the previous work that's been done in the Burdekin catchment. Also, some of our work looking at the different sediment sources in the different Burdekin flood plumes over the years, we can clearly pick out different sources from the Burdekin catchment. So, for example, in 2017, we had a plume dominated by the Bowen Broken Bogey catchment, and you can see these are the black dots falling out there in the plume. In 2018, it was really dominated by the upper Burdekin source, and that's really these red dots here. But we also see a mixture of sources that we're currently under development to untangle finer tributary sources in the Burdekin. So I think with that, I don't know how long I've gone, but thank you.
Great. Thank you, Steve. Halton, did you want to?
Yes, thank you, Jane. It doesn't seem to, we don't seem to have any questions for Steve's presentation at present. So unless anyone does have a question that they wish to submit, we can move on. If you do think of a question, feel free to put it into the chat.
So welcome back, everybody. The second half of this session, we're going to hear more about the catchment side of things in terms of management options. We're going to hear from Rebecca, and then Andrew's got a longer session because he had several NESP projects. I couldn't convince him to condense it to 10 minutes. So anyway, we'll start with Beck, and Beck, I'll let you know when you've got 5 minutes to go.
Okay, great. Thanks, Jane. Can everyone hear me? Is that okay?
Yep.
Yep, okay. So this morning I'm going to run through the extension of 2.14 project for NESP, which morphed into 5.9. So basically 4 wet seasons. Importantly, this project is co-funded with NESP, but it's also got a strong influence from the Queensland Government Landholders Driving Change program. So just acknowledging the research team, the support team, mainly from NQDRI Tropics and Damon Telfer and Queensland Government, and then the funders listed there below. So as with others, the schematic diagram that we're sharing just shows that we're now moving back away from the salty bit up into the catchments. And I'm going to be covering mainly hill slope and alluvial gully erosion, not so much touching on hill slope or bank erosion today. So today I'm presenting on gully remediation, but so is Andrew after me. And I think the important distinction here is what Andrew will be presenting is largely gully remediation within the larger alluvial systems, so trialling within those systems. What I'll be presenting today is more of a spectrum from the smaller, cheaper gully remediation right through to the more expensive, large-scale mine site remediation. And some of the logic here was that we were looking to see if there were any options that farmers might be able to do themselves if they were interested and had a big gully erosion issue. So projects ranging from about $3,000 through to about $1 million. The sites in red that you'll see on this map on the left are the project areas I'll be talking about today. So 2 in the upper Burdekin and a few in the Bowen and some in the Bogey and 1 in the Don. For context, in the Burdekin, the purple dot is Strathalbyn and blue is Havilah, one of the new sites that is hopefully going in very soon. So just stepping to the side before I get going on our local results. When I first started this project, and often what I do starting most projects is actually head to the library, trying to find out what actually other people have done all around the world in terms of gully remediation. It's not unique to the Great Barrier Reef catchments, right around the semi-arid tropics around the world. It's a problem. And worked with some colleagues in Belgium to say there was actually a gap in the literature on our understanding of how to treat gullies and what effectiveness we will get from those treatments. So we put together an international literature review, which is listed there at the bottom and is available open access online for anyone looking for an early Christmas read. It's a fabulous document to put in someone's stocking. If you don't have time for that, 2 key messages are probably you will get a decline of sediment yields faster from gully remediation when you treat both the catchment above the gully as well as the area within the gully. And the other key message is that you're likely to need some engineering, soft or hard engineering, plus vegetation. But in the long term, and some of the really long-term studies from Middle East and Europe suggest that it's the vegetation that is the key, because often the engineering structures will fail within 10 to 20 years. So with that knowledge in mind that we captured in that review, we set up the trial site. So today I'm covering 7 sites and all of them have the same setup. Each of them have a control site and the treatment gully. And this one here's an example from the Strathbogie in the Bogey catchment. And at all the sites we measured vegetation and land condition. We measured terrain, and that was done using different techniques. We were trialling the Zebedee SIRO scanner. We had Queensland Government's terrestrial laser scanner, and in some cases LiDAR. Then the integration of the condition of the gully and the catchment is expressed as water quality and runoff. And if you get decent amounts of data, we turn them into sediment loads. And loads are the key thing we're after here, because that's generally what people are paying for in terms of abatement or reduced sediment delivery to the marine system that we've heard from the previous talks. So just a few more pictures and another slide. This is an example from Minivale in the Don, but just showing the style of monitoring that we have at all the sites. So we generally, up in the top right is the cover and biomass and species composition data. We measure that on the hill slopes and within the gully. This is an example of the terrestrial laser scanner, then the Zebedee scanner, and then along the bottom is the water quality monitoring set up with the sensor cluster, which is generally continuous depth and turbidity, and then the samples are collected often by helicopter because that's often the quickest way to get there, and then the samples can be processed for suspended sediments, nitrogen, particle size, and in some cases genomics, depending on what we want to look at. I suppose the key thing a lot of people are after at the end of the day for things like the Great Barrier Reef Foundation and other groups trying to work out where we should prioritise investment is around how cost effective things are. I'm not talking about cost at all today, I'll leave that with the economists, but the effectiveness value is quite tricky to come up with. In this particular study, we've what I'm calling a gold standard method for effectiveness, and it's not what we'd encourage everyone to do everywhere because it's expensive and time consuming, but it's really important for publishing and getting that definitive data about what works and what doesn't. And to do that, you need probably 2 key things, a control and a treatment site, and preferably where you can before and after data, before and after that treatment. If you don't have before and after, you can actually detect changes over time, but you're just going to need a longer data set. And that's probably, a good example here is from Mount Wickham. You'll see on the right here is the treatment data in green, and you'll see the before data and then 1 year after data. And actually there was a significant difference in the sediment concentrations in those 2 years. And had we not had a control site, we would have probably falsely said that that result was due to the treatment. In fact, we look at the control site and we now know that that effect was purely just because of rainfall and runoff variability. So there was no treatment effect that year. We are working in highly variable climate conditions in these landscapes and we need that control site. The good news is the third year, we were able to see that the control still remains really high, and we had a significant effect in terms of the treatment working to reduce sediment concentrations in that next year. So just an example of why we need this rigour to get that, to pull out the climate variability, which is actually quite critical. A big slide with lots of information, but this is the key to tell you that in the report that the draft came out in June and the revised version should be online soon. I've synthesised into one table all the data we have from the 7 sites. Actually, there's 14 individual gullies here, and then tried to show how things have responded in terms of those attributes that we measured. So land condition, erosion rates, concentrations and loads. And then using that, what I'd call the gold standard effectiveness value, we have a number of sites where we have quantified whether the remediation has worked. In other cases, we've had really interesting insights as to whether it's worked or not, but statistically we're not quite there yet to be able to say definitively at all sites because of a range of reasons. Some not having before data, some having very little runoff in some years, some instrument failures. I'm going to give you a couple of insights into those just two of those sites in the short talk we've got today. But another thing that's been really useful to get the spread of, small and big gullies is to start seeing how sediment and nutrient concentration data varies across the different types of gullies, which has been really interesting. We get much bigger ranges in sediment concentration data than we do in nitrogen, but you can look in the report for more detail on that. So just quickly, a couple of snapshots from 2 of the case study areas. Mount Wickham, many people online are probably familiar with. This is one of the landholder driving change case study sites. It was a large alluvial gully that was, the remediation design was done by Batira and Alluvium, so we didn't have a lot of involvement in what went on in the program, but we did the monitoring. The red arrows here will show you what it looks like before and now after. So there's significant change in this landscape, but also significant investment on the ground. But the good news is it gets the gold star in terms of it has had a statistically significant change. But one of the things that's interesting is you will get a different number depending on the data set you use. So on the left here, we've just used the raw concentration, sediment count concentration data, and we get an effectiveness value of about 93%, so that's pretty good. But more robust is to normalise that data against flow, which reduces the effectiveness value, and more robust again is the loads data, which drops it back to 0.85. But overall, I think, if your kids came home with a report card with any one of those numbers on, you'd be pretty happy. So, but what we're saying is effectiveness is greater than 0.85 at the moment. And the loads is where we want to get to because that's what people are paying for in terms of abatement. And at the end of the day, whoops, the picture speaks 1,000 words here. This is the difference we're now seeing in terms of samples coming out between the 2 different sites, the control and the treatment. So just touching on Strathbogie, and this is a lovely example of completely different sites. This here is a linear gully, not an alluvial gully, and it's on very different soil. So this is on a vertisol, very fine material that is likely heading out and landing on Kath's seagrasses and in Steve's loggers. So, and the other thing, this is very different. So the actual remediation work's done here, it was very bottom up. This was landholder led, not a big engineering firm coming in. We also have 3 years of baseline data here, which is fabulous from a scientific perspective and just luck really. So it showed us that this gully was moving very rapidly. So this here on the right is the GIF from the terrestrial laser scanning over those 3 years. And then we were able to capture a lot of events over 4 wet seasons through at this site. And these 4 images just show the difference between the control on the left and the 18-19 wet season at the top and the 19-20 wet season after the remediation went in on the treatment site. The treatment site, the peak event in 18-19 on the top right, and then in 19-20 after the remediation that went in, which was largely about hill slope diversions, there was actually no samples collected and no runoff recorded at this site. So essentially erosion was halted after that remediation work. So statistically, Climate, thanks, Jane. So statistically, this site also gets a gold star, but with a couple of caveats. We only have 1 year of post-treatment data here. And so we're concerned that the hill slope bunds may breach over time. And so we would like to keep monitoring here for a few more years to see if it stabilises. So we've put great job, but watch this space on this site. In terms of key outcomes, we've also been sharing data with some of the marine studies, because at the end of the day, it's really important that the samples that we're collecting back up in the catchment are connecting to the marine system. Otherwise, the remediation's not really worth it. So we're making sure that, that there is a link there between the geochemistry and the particle size. And we've also been sharing samples with the Queensland Government in terms of the bioavailable nutrient work. What is that? Far out. Sorry, my computer wants to do lots of updates. So I suppose the questions now are around how long do we keep monitoring for? I don't have the answer. I'm very conscious that, that this type of work is expensive and very time consuming and remote and challenging. But I think we need to keep in mind monitoring has several purposes. One is to evaluate the performance of these expensive remediation trials that are actions that are going in, and we've been doing that. But the other thing is to learn about processes, which we've been doing a lot of, and we've learned a fabulous amount about gullies during the last 5 years. But the other really important thing is about engaging people, and these sites have now become critical for informing the Landholders Driving Change project in the Burdekin, and that's being extended out to other parts of the GBR where there's gullies are prevalent. People are learning a lot. So some of the other benefits of gold standard monitoring is that when we collect samples, we can do lots of things with them in the lab, so it has an added benefit. The discharge at the end of the day about getting understanding how much runoff is occurring at these sites is really challenging. As you can see here, some of the sensors regularly getting smothered during the big events. But if we don't capture that runoff data, we're missing probably 80% of the story in some of these catchments. We still need to collect multiple lines of evidence. I don't think we've landed on any one technique that it's going to give us all the answers here, because some have the strengths and weaknesses under different climate conditions. So we need to keep that up. And because of that, the cost effectiveness values are going to fluctuate a little bit for some of these sites as we get more data. But overall, I think we've done a good job at providing peer-reviewed publications for the next consensus statement and any future Senate inquiries. So the final slide is just, there has been about 11 papers come out and are attributed to this work. The key ones highlighted in orange there. And if anyone's interested in any more information, just ping me an email and I can send you copies. Thank you.
Excellent, thank you, Beck. Right on time. We've got time for a couple more questions if people have anything for Beck.
Alrighty. Okay, so look, as sort of Beck's already given an introduction, I'm really focusing on a couple of large experimental sites that were focused on testing the effectiveness of large-scale alluvial gully remediation. So firstly, I just want to just acknowledge there's a whole team involved in this, and both of the projects that the sites that I'm presenting today are collaborations. The first one up in the Crocodile Station in the Cape is a collaboration with Cape York NRM, and that one's funded by the Reef Trust, the on-ground works component. The second site is at Strathalbyn in the Burdekin. That's a collaboration with Greening Australia and the Queensland Government. And so there's a whole other cast involved there, you can see on the slide. So similar to what others have highlighted, we're focusing here on the gully systems, some of the key sources in the GBR catchments. You'd be aware that in the large dry tropics catchments, gully erosion can contribute a significant proportion of the fine sediment to the GBR. varying depending on subcatchment by between something like 40 to 60% in some subcatchments. And this comprises both hill slope and alluvial gullies, and Bex mentioned both. I think by now most people should be getting the hang of the idea that there are these really fundamentally different types of gullies. The hill slope gullies, there's sort of smaller, more linear ones up on the slopes, and then these big, and they're not always big, but typically they are pretty big down on the flats on the alluvial plains. So today I'm focusing on these big alluvial systems. So what we set out to do in this project was really to set out through a couple of experimental sites to measure what the erosion control effectiveness is of large-scale alluvial gully remediation. Also, how long does it take to achieve that sediment reduction? How resilient are these treatments in large events? And we do have, fortunately, we've had a few large events now. We've been monitoring sites for up to 3 years, and we've had some pretty good wet seasons. So we're starting to get a bit of an idea on that. I'm also going to very briefly touch on the bioavailable nutrient reduction side of the story, and very quickly on the cost effectiveness side. So as I mentioned, we've got 2 sites, one up in the Cape at Crocodile Station, and the other one at Strathalbyn in the Burdekin. So just quickly looking at the Crocodile site. So this is a site where we've got paired catchments, or gully catchments, if you like. There are 5 gully systems, one of which is a control, and 4 other treatment sites. So this is what they look like on the ground. This is the control site. And this is the sort of treatment that was done. So we're talking about major engineering earthworks, where we're doing complete gully reshaping, treatment with gypsum and capping and so on. This is what it looked like after the first wet season at this site. And again, from the air before and after the first wet season. So as Beck highlighted, at these sorts of, given this was a fairly major experimental site, we implemented a whole range of sampling and monitoring techniques, both measuring water quality using a range of different measures, most of similar sort of things to which Beck outlined. I guess the only different one here is that the inclusion of this thing called the PASS sampler, which was an integrated sampler developed by Nick Dorian, who was doing a PhD through this program. So he developed this new integrated sampler, which has proven to be pretty effective. Then you can see the other range of monitoring techniques there. I'm happy to provide these slides. I'm going to be going through this fairly quickly, so if you miss some of the detail. The Strathalbyn site is a larger site again with 8 different treatments and a couple of sub-treatments within that. So there's 10 sites all up. Total gully area in this site of around about 18 hectares. One thing I just want to point out here is that the graph on the top right here shows the annual rainfalls through the monitoring period. So we've had quite a range. We've had some quite below average years, but also some significantly above average years. The 2018-19 wet season in this area was the 6th wettest on record, and that's over 120-year record in that area. So, and that occurred the first year after a lot of these treatments were done. So it was almost a sort of a worst case scenario in terms of a test for these treatments. Again, at this site, a whole range of monitoring techniques. I'll just highlight that there's a range of both topographic measurement techniques, so using various types of LiDAR measurement, as well as water quality monitoring. At this site, and I'm not going to go through this in any detail, but just to point out that there are a range of different treatments, and so there's a whole range of different approaches applied in different gullies. I don't have time today to go into the nitty-gritty detail of what came out of that, suffice to say that there are a range of different things, from sort of more expensive treatments to sort of lower cost treatments. So this is the sort of thing that it looks like from the air and ground. Major earthworks. You can see, if those with a keen eye, there's actually an excavator and a truck there. So these are large scale sites. And so this sort of builds on the idea of it's kind of like, in some ways, similar to the sort of things that are done in mine site rehabilitation. And that's kind of a conclusion that came out of a previous project that we did, looking at approaches to doing this sort of scale of gully rehab. So just quickly, some results. And I'm just going to fly through these just to highlight some of the key points. I think the key thing to take from this slide is this site 2.234 is the first treatment area. The green dots here are the control. So on this site, this is after 2 years, there's been an order of magnitude reduction. These other 3 treatments are not so great in the first year, starting to improve in the second year. I'll explain that a bit more. I guess the key thing there was that those treatments were done too late in the dry season, and they got caught out that year with some early wet season storms. And so the water quality improvement for those particular treatments was not great in the first year due to that. It's improved by the second year post-treatment. You can get a sense of that from this plot here, which shows a trend through time over 2 years. The red and the darker lines here represent those other treatments, and you can see that in the first instance, the sediment yield from those gullies actually went up above the baseline. So a bit of a lesson there in terms of not working too late into the dry season, or where you're going to potentially get early wet season storms. This is some of the LiDAR data showing the sort of changes we observed, and this is the cumulative change across 3 years. The blue represents deposition and the red erosion. At this particular gully, we've had a net sediment deposition across the 3 years of monitoring. So the erosion control effectiveness here has actually been greater than 100%. As Beck pointed out, the way we measure the effectiveness is to compare in terms of both a control and a treatment, or a control and impact, and then before and after, when we've done both things at all of these sites. What we also do is for each of the treatment sites, they are adjusted for the relative erosion, background erosion rate compared to the control site. So you can never find 2 gullies that are identical, but if you can adjust it, you can get a more accurate assessment. Just in this slide, a couple of things to draw your attention to here. So this is this gully 234. After 2 years, or this is actually after 3 years, we're seeing more than 100% effectiveness. But these other 3 sites, as I mentioned, very poor result in that first year. They actually went significantly backwards. But by the next year, you can see the effectiveness of those 3 sites had improved markedly, up to sort of somewhere between 60 and 95%. One of the things that's come up through this work is that these big alluvial gully systems are actually also subject to backwater from the rivers that they're draining into. So I'll just show you some images, and this is a good example to show the sort of resilience of these treatments. So this particular gully here, this sequence of photos shows, has had a significant backwater effect. So 4 meters of water from the river went over the top of this gully. And yet a week after that, you wouldn't even know that it occurred. So this is a real real issue with these gullies. One of the things that we've realised, we didn't quite appreciate how frequently it occurred when we started this, and the data that we've gathered from this site shows that this particular site pretty much goes underwater every 2 to 3 years. One of the other interesting things is that we also see that in about the start of the 1990s, we're starting to see much higher floods. Don't know what is really driving that, but it could actually have been the trigger for these particular erosion in these gullies. Just moving on to the Strathalbyn results. Again, some data from some water quality monitoring data. In this case, we're seeing 2 orders of magnitude reduction of suspended sediment concentration. That's after 2 years. It pretty much occurred in the first year. Not in this site. This 2017-18 there is a sort of a before data set. So in 1 year, we're seeing 2 orders of magnitude reduction. Converting that into loads, we're seeing a similar sort of response. I won't go through that in detail, but yes, between sort of 2 to 3 orders of magnitude reduction in sediment loads. Just some of the LiDAR data, just quickly, just to show you the sort of changes that we've observed, and this includes the response associated with the actual construction. Just to show that it wasn't all perfect, this is an image that shows some erosion that was triggered by, there was some cattle accessed this site during one of the wet seasons. You can see those rills that are formed through the gully there are actually associated with cattle tracks. So this is something that we're going to be discussing more through the Reef Trust, is this whole idea of cattle access to these sorts of treatment sites into the future. Some summary results on the effectiveness data across all of the treatments. And I won't go through all this in detail, but just draw your attention to the fact that these key sites here, the overall treatment effectiveness was in the high 90s. There's a couple of lower ones. This treatment 6, this was the one that was sort of treated to the lowest level possible. And it's had an effectiveness of somewhere between 50 and 80%, depending on how it's measured. This highlights that data again. You'll see, depending on whether you're using the water quality monitoring data or the LiDAR data, you do sometimes get different results. This particular one that I've highlighted here shows that there are issues with just relying on LiDAR data, because in that first year, there'd be a whole lot of erosion just from the construction work that would actually be below the level of detection of the LiDAR data. So the water quality monitoring data picks up the response a little bit better in that case. So just to summarise all of this at the 2 sites, so the overall sediment abatement that we've had at the Normandy site has been 165 tonnes. Now that is affected by that fact that we actually had an increase in erosion from 3 of the sites in the first year. So if we hadn't had that overall result would look a lot better. In terms of what proportion of the catchment water quality target that represents, what we're saying is we need to treat about another 60 sites at that level of intensity to achieve the water quality targets at the catchment scale. In the Burdekin, with the Strathalbyn site, it's by the start of this year, we'd achieved a net result of 4,400 tonnes of fine sediment abatement, and this is at the coast, this is at the reef. And so that's a pretty good result. That's about 0.8% of the catchment target. So we need to do another 129 sites on that sort of scale to achieve the catchment water quality targets. Very quickly, I just want to quickly go over the nutrient results. The key message here is at the Crocodile site, the nutrient results pretty much matched the sediment reduction results. That's the key take-home message there. From these plots here, which plots the nutrients against suspended sediment concentration, you can see there's a pretty good relationship, particularly for the particulates, as you'd expect, against the suspended sediment concentrations. The dissolved nutrients are a little bit more complicated, but there's still a reasonable relationship between suspended sediment concentration and the dissolved nutrients. Now, at the Strathalbyn site, it's a bit of a different story. The particulates, again, essentially follow the trend associated with that we see from the sediment reductions. However, the dissolved nutrients in this case have not gone down. They've actually increased compared to the baseline, or sorry, the control. What we think that's about is the fact that there was a lot more organic matter and nutrients added to those treatments as part of the treatment process. And so we're seeing some leaching from those organic additions to as part of the treatments of the sites. There's some ongoing research looking at this now to actually get to the bottom of what this is, but the trend is still there after 2 years. So we would expect that would decrease with time. So that shows when we plot suspended sediment concentration against the various dissolved nutrients, we're seeing the relationship is going all over the place here. So that's the subject of ongoing research. Finally, I just want to quickly look at cost effectiveness, and this is using there are two ways of measuring cost effectiveness. I'm not going to go into that now, but this is measured at the end of gully across at both sites, and you can see that there's reasonable comparison between the sites, even though they're quite different sites. Something between $30 to $80 per tonne. Now, this is a different metric to the dollars per tonne per year, which is used in the Reef Trust. We've also got the other data in the report. All right, I'll leave that one there. Any questions? So this is, are you seeing that okay? So another separate project was about mapping gullies in the GBR catchments. And so this is a project that was designed to develop a method for objectively mapping gully systems from LiDAR data sets in the catchment. So very high resolution to help us with targeting. So we'll have a LiDAR data set that might look something like that. What we need to do is take it from that to the image on the right, where we've actually identified the gullies, and we can actually quantify what's going on in each of those gullies. So this is the objective of this project was to efficiently and objectively map gullies over large areas, so thousands of square kilometres. There's a whole range of ways we can do this. What we start off doing is mapping what we call eroded landscape features, or ELFs. So I'm going to talk about ELFs. ELFs are just, there's a whole lot of different eroded landforms out there, not all of which are gullies. So, or active gullies. So what we do is we start out mapping these things, and then we have to filter out and work out what out of that is useful to know about. So we've derived this whole approach for doing this. I'm not going to go into it. What we have to do is treat different parts of the landscape separately. So alluvial gullies are involve a different mapping process to mapping hill slope gullies. So there's this whole process for dividing up the landscape into different types. and then mapping the features within those. And so this is what the process looks like. It's an automated process that firstly identifies areas in the landscape that it thinks might be a gully, and then it goes through a detailed process to actually map those features. The key part of the whole process, though, is just mapping these, what we call ELFs, is a fairly simple process. The key thing, though, is filtering out what actually in that is actually a gully that is actually eroding and contributing sediment. And so there's a whole process we go through for weeding out ELFs into actual gullies. And just to give you an example, so this is a block in the Fitzroy. This is the first pass of the mapping, which you can see maps a whole lot of things across the landscape. We then go through a three-phase filtering process to bring it down to something that is actually meaningful to us. And this is the final step of that process. You can see there's a much more distributed set of features in the landscape. So in that particular block, what that boils down to is there's 630 odd alluvial gullies, 945 colluvial gullies, and what we divide the hill slopes into two different categories. Typical colluvial gullies or hill slope gullies, and then features in much more rugged terrain, which tend to be a lot less active. The actual areas, though, are quite different to the numbers. So there's much greater number total area of alluvial gullies compared to colluvial gullies and these rugged hill slope gullies. The way this is currently done through the NRME is using a presence-absence visual mapping approach. The map on the right shows what that looks like. The map on the left is our output for the same area. You can see the LiDAR block indicated there. Now, there's some, reasonable similarity there, but when you get down into it, there's quite a bit of difference as well, because we're mapping this at much higher resolution. There's some of that in that particular block, just highlighting that, the gullies by number and gullies by area for those various categories. So the key part of the process that we've developed is this filtering process and identifying which of the mapped features are actually active and ones that we'd actually want to target for rehabilitation. So we've developed this other metric, which we have called the potential active erosion metric, which identifies the actual gullies that and their potential activity.
Andrew, just can you go for just a few more minutes? Is that okay?
Yep, a couple more, that's it.
Thanks, yeah.
So this is some data which compares at a selection of 645 gullies where we've actually got measured erosion rates from LiDAR DEMs of difference, comparing it with the PAE process. And you can see that there's a pretty good relationship between the LiDAR DOD estimates of gully erosion and the PAE metric. And this is from a single pass of LiDAR. So what we have here is a potential tool for identifying gully activity just from a single LiDAR pass, which is quite a significant sort of innovation. This is what it looks like close up. So the image on the left is the LiDAR DOD data. So that's actual measured erosion, and the one on the right is the PAE metric. A couple of other features of the mapping work. We've also developed a method for reconstructing the prior land surface across the whole landscape of eroded gullies. And so this is what this is showing here. And that allows us to then come up with another way of determining the whole of life erosion volume from gullies. So across the whole area that we've mapped, we can come up with the total lifespan gully erosion volume, if you like. When we combine that at particular sites with air photo data, we can then come up with these trend lines to show the erosion rate at a particular site. Some other work we've done as well at a selection of something like 65 sites. We've got detailed air photo analysis where we've actually reconstructed the start dates of these gullies. And what we've found is that the average start, and this is in the triple B, what we've found is that the average start date of all gullies is about the mid-1930s. But when you look more closely, there's two cohorts. There's an initial cohort around the late 1880s, and then there's a second cohort in around the mid-1940s. So the immediate post-war period. And so from that, when we're using that gully commencement timing with the total volume timing, we can actually come up with total erosion rates for gullies across large areas. Just finally look at this. This is some data from the triple B. When we look at all of the erosion rates of gullies across the whole catchment, what we found is that around about 30% of the total sediment yield is coming from 2% of the gullies. And these are typically alluvial gullies. And then 50% of the sediment yield is derived from just 6% of the gullies. So it's really important then to just bring it back to our original conceptual model. When we look at the hill slope and alluvial gullies, it's really important to be able to identify and target that 6% of gullies for remediation that are contributing 50% of the total sediment load. So just to summarise, we've mapped now a total of around about 5,300 square kilometres of land area in both the Triple B, the Fitzroy and the Laura and Normanby. We've divided this up into these 3 different landscape units. And I think we've now got a pretty viable sort of method for rolling this out across large areas. We've put a lot of development into actually automating the process, and it's now a pretty efficient process. And I'll leave it there. Thank you.
Thank you, Andrew. So we do have a couple of questions here from the chat for you. The first one is from Maria Vitelli, and she's made a comment about ripping grazing soils as a method to address pasture rundown, especially for buffer pastures. And the question is it possible that soil disturbances at Strathalbyn Station released nitrogen and phosphorus from the soil due to a mineralisation effect as a result of ripping those soils?
Look, yes, it is possible. That's something that we're just investigating. So we've got some work going on this current wet season to look at that. So we're using a range of tracing techniques to actually get to the bottom of that. So it's but it's probably a combination of potentially that aspect, but also more likely the bulk of it is due to the organic addition to the gully treatments themselves. So there was straw mulch, there was bagasse, and so quite a bit of nutrient addition to the systems, which is most likely the source of that elevated dissolved nutrient load.
Thank you, Andrew. And the second question from Murray again is in regards to the PAE gully tool. Is it going to be used by the Queensland Government DES compliance staff, or is the PAE currently a research tool only?
Well, it's certainly currently only a research tool. I guess that's up to them. I couldn't answer whether that, but it is. Look, it's just about to be submitted for publication. So I guess once it's been published in the scientific literature, there's nothing stopping anyone from using it. But you know, look, it's potentially a great tool, and you know, we're not saying it you know, outweighs, you know, doing sort of repeat LiDAR or other monitoring methods, but as an initial first pass to get a sense of erosion activity, it's a very useful tool.
Fantastic, thank you, Andrew. Now, Jane, would you like to take over and finish with some highlights and conclusions if we don't have any other? Oh, we've got a comment here from Chris just saying that DES compliance is currently looking at ground cover remote sensing products. Focus on compliance is ground cover on paddocks rather than gullies. So that addresses that aspect of it.
So I'm just going to go through what I've gleaned as the highlights from our reading of the research reports. I should recognise the efforts of Murray Cum Panita that has done most of the work into the technical report. We've used this landscape diagram to frame the story, and we're working from the sea back, looking into the sources and management options. So I've grouped the conclusions that I've received from the project leaders into three main elements. So the sediment, fate and impact story, the transport and source type story, and then the management response story. So I'll just go through those. The highlights in relation to sediment, fate and impact in the Great Barrier Reef. So to really need that better understanding of sediment impacts on the GBR ecosystems and the sediment to sea source, sea to source connections and interactions, so that we can guide the management responses back in the catchment. And so to support that, this work has delivered a refined understanding of some of the important sediment interactions in the marine system. So as Steve and Catherine and Barbara all described, it's the increased suppression of light in the shallow, turbid environments during flood plumes and the months afterwards that's really important. But we're also learning that for that considerable impact to occur, it typically requires a few large events of consecutive flooding over 2 to 3 years, and that's what they've highlighted in their Burdekin studies. It's also showed the influence of pulse delivery of flood plume sediment and particulate nutrients to inshore coral reef sites is really important, and the linkage to that that you get with an increase in macroalgal cover and in some areas deposition of marine snow. And then the other point they've showed is that the chronic persistent turbidity, and then as a result of that, the reduced photic depth and light occurs for long periods as a result of that considerable disturbance and resuspension or new sediment delivery in areas of poor flushing. So there's some areas where you will get that long-term chronic loss of light, and we're understanding now the implications of that for the ecosystems in those areas. So some of the work that has been progressed in that we've heard about, so the new water quality index that Barbara's proposed and explored, it could be considered for application in the GBR. It relates directly to ecological impacts, and it also considers those chronic effects of light stress. Catherine's team established the ecologically important indicators for seagrass and the light threshold specifically. They've also defined desired state, which is so important for establishing targets and objectives for Great Barrier Reef ecosystems. So what is it that we're aiming for? So they've had a go at that for seagrass. They've figured in relation to the interaction between loads and seagrass health, the primary driver is really about interannual changes and multi-annual loads, not just single years. And they've provided some assurance for the existing load targets, which is a relief, not by coincidence though, and by comparing scenarios with the proposed thresholds. There's a whole body of work that we haven't described today looking at cumulative impacts of multiple stresses. So Sven Yipicki and his team from AIMS have looked into that. It's described in the technical synthesis report, but it describes those important interactions between say reduced light from sediment impacts and other influences such as responses during temperature events or other disturbances. The other next part of the story is really about what do we understand looking back towards the catchment, how the sediment moves from the catchment to the reef, and knowing more about the most important sediment characteristics for ecosystems enables us to target management efforts in the catchment. So understanding how they're transported from where and when, and then which bits are most important in the receiving environment enables us to prioritise our management. So Steve and Zoe and their teams use the tracing to identify, I guess they're calling it the most damaging sediment sources. It's the fine materials, it's the organic rich sediment that travels furthest in the GBR, and it has the capacity also to release dissolved nutrients and influence turbidity and macroalgal responses. Particularly in the inshore GBR. So some of this stuff probably is sounding very familiar to you because this was probably established earlier in their project, and it was, I guess, a major finding in the last scientific consensus statement, but their more recent work has built on that and confirmed that understanding in more areas. We've also identified that plume sediment is dominated by subsurface erosion sources, so that's the tracing work that they've done, which it links back to then, okay, what types of erosion do we need to be targeting in the catchments? And then they've measured the release of dissolved or inorganic nitrogen from sediment plumes, and in that identified that there's quite a significant contribution of nutrients from the particulate nitrogen, particularly in those in the early stages of plume development. In terms of management, so the most cost-effective management options are going to vary between catchments and landscapes, and the selections of what is implemented needs to be supported by the high-quality evidence. And I think we've heard from the projects and your understanding of this work as well is that this research has really generated some foundational knowledge to accelerate what we do in the catchment for sediment reduction, particularly in high priority areas. So Andrew whipped us through his gully characterisation framework, which has been applied now in detail in the Bowen-Bogey-Broken catchment in the Burdekin, which enables us to prioritise effort in the landscape. So as we've seen, it can be an expensive exercise to remediate some of these gully and streambank erosion sources. And so having that characterisation and understanding which are the most important aspects of gully formation and development that can be targeted is critical going forward. Some of those characteristics are obviously the fine sediment story, particular soil types, and then also the contribution of those soil types to both fine sediment but also particulate nutrient sources. Andrew's also assessed the diversity of gully forms and identified that not one size fits all. We're going to need a whole range of interventions, and as Beck highlighted, there's some learnings from overseas where from both small scale and large scale interventions that have been applied. So both Rebecca and Andrew's teams have investigated what are some of the most cost-effective remediation techniques at various scales. So at, I guess, the smaller scale, porous check dams, working with sticks and logs in combination with exclusion of stock appear to have a major impact on the amount of vegetation that can then stabilise the gully floor, which then in turn leads to stabilisation and reduced sediment erosion. As was found in the international literature and confirmed here, treatment of the surrounding catchment area is absolutely critical. In some instances, depending on the land use and the landscape, but in many cases, the reduction of grazing pressures within and around gullies is going to be really important, particularly in the period close to treatment and for the, I guess, the wetter months following that. When you're looking at the larger systems, the large-scale engineering solutions that have been trialled by both teams have been proven to be successful in reducing sediment loads, which I personally think is a huge relief and a huge finding. It delivers potentially short-term, relatively short-term outcomes for sediment reduction. And yes, it is expensive, but I think that now the establishment of the techniques and the strong evidence behind it means that there is confidence in future investment in that work at a larger scale. The total erosion rates vary considerably among the different source areas and the sampling years, with the higher rates among the alluvial gullies, channel banks and beds. So we are still working in a situation where we can't just apply these results everywhere, in terms of assuming that yes, this kind of thing is going to exactly work here. We need to understand each landscape, but we do have good confidence now in the methods at various scales. A really important point came up by Beck and Andrew. So the costs of treatment vary between locations and methods, and what keeps coming up in all of the discussions, both within the research projects but in the on-ground works as well, as there's an urgent need for a standard cost-effective metric across investment programs. So each program has a slightly different method for good reasons, but there is an identified need to make that consistent and a minimum information requirement. So that was my attempt at providing some highlights in terms of how has the research informed management that we're aware of already, and obviously we're hoping that this research has legacy and continues to influence management. But just a few examples, and this is fleshed out in the technical synthesis report. So there have been direct reductions in the end-of-catchment fine sediment loads through the work that's been done on stream bank and gully remediation projects. So while they've provided a very neat experimental platform, they've also delivered good outcomes for sediment reductions. There is a potential reduction in ecosystem impacts that could also be expected from our improved understanding of which types of sediment we need to be targeting, our understanding now of nutrient bioavailability in moving from the catchment into the marine system, and then the light limitations and those dynamics in coastal ecosystems. Also a raft of improved water quality monitoring tools and protocols, and then the application of new indicators of ecosystem health that could be applied within monitoring programs over time. The work is already informing existing investments and investment decisions. So the Reef Trust Partnership and the Burdekin Major Integrated Project, they're both partners in this work, but also they have benefited from the outcomes of this work, both in terms of what are the best options, how can we better inform site selection and prioritisation, so we're targeting our effort, what are the best monitoring and evaluation techniques given different situations, and then also just that variability in treatment options depending on the landscape and how that will affect cost effectiveness. This sort of research will inform the review of the Reef 2050 Water Quality Improvement Plan sediment reduction targets, particularly the seagrass work that Catherine's done enables us to, well, A, have confidence in the existing targets, but also refine them when the opportunity comes up to look at those range of thresholds that they've developed. And it's also going to be work that can be incorporated into the next scientific consensus statement and the GBR outlook report. So on that, all of the work is being externally peer reviewed by at least 2 external reviewers, and the synthesis products will be reviewed in a similar way. Just to cover, so you know what's happening with next steps and the timing. So at the moment, researchers are finalising research reports. You've heard a few of them refer to the deadline next week, and they're also being asked to review the technical synthesis report. The case studies that I mentioned earlier are being finalised for production in various forms. The website is still being built, but we will have a demonstration of that next week, and it'll continue to have material added to it. And then this group, we were hoping to do something like this earlier this year, but constrained by travel restrictions. But so we're hoping that in April next year, we like to run a forum to provide a showcase of the synthesis products that are developed, and then a bit more detail on project outcomes. So I realise some projects have had the opportunity to do that through individual seminars. This forum is proposed to give each researcher a little bit longer and linking that story between projects so that we've got a bit more of an integrated picture for managers. So keep tuned on that one. We will be circulating dates in the next little while, but yeah, that's to look out for. So we do have a little bit time for more questions or additional comments from the researchers before we wrap today. But I just wanted to say a special thank you to the Hub Liaison team and also RRC for coordinating this presentation and enabling us to give you a snapshot of the work that will be combined into the sediment synthesis.